Predict all the alkenes that would be formed by dehydrohalogenation of the following halides with sodium ethoxide in ethanol. Oh my God. And identify the major alkene. Now we are talking about an elimination reaction called dehydrohalogenation. Now this is a very important reaction, and before we go around solving these problems, let me just give you a quick brief about it. What is the meaning of dehydrohalogenation reaction? D means removal. Hydro stands for hydrogen. Halogen obviously stands for halogen. Dehydrohalogenation means removal of hydrogen and halogen. Means removal of HX. Please note in this case, H is attached to one carbon and X is attached to the adjacent carbon. So, removing H and X together, the H plus and X minus together from an alkyl halide, to produce the alkene, this is called dehydrohalogenation. Please note, this is called an elimination reaction. For this, you need a strong base like sodium ethoxide in ethanol or alcoholic KVH. Yes. Anything else? There is a rule also when we talk about the major product, and that is called Zaitsev's rule or Zaitsev's rule. The real name is Zaitsev, the Russian scientist, but British started calling him by funny names like Zaitsev, and that has become popular. So it's the same person, Zaitsev. We'll just take up one example and exemplify what the rule also says. First, let us look at the first question. Methyl cyclohexane. Now, first let's take a cyclohexane molecule. 1 bromo, 1 methyl cyclohexane. Lovely. And when we talk about dehydrohalogenation, there is a method involved. And what is that method? See, listen to me with great concentration, simple method, you'll find it very useful. And then we will come to Zaitsev's rule also. Br is going to leave, right? And the carbon atom to which Br is attached is sometimes called alpha carbon. What? Let me repeat. The carbon atom to which halogen is attached is called the alpha carbon, right? And the neighboring of alpha is supposedly beta carbon. So what are the neighbors? Alpha, this is beta, and this is also beta. Oh my God. And the concept is that the beta hydrogen is removed by the base in dehydrohalogenation reaction. What? The beta hydrogen is removed by the base in dehydrohalogenation reaction. Okay. So, which hydrogen? Are the hydrogens here? Of course. If you see, this is HH, this is HH, and there are 3 hydrogens. So, if you call it beta 1, beta 2, beta 3, there are 3 possible locations. And by the very design, because of symmetry, beta 1 is same as beta 2. So when you cause the elimination reaction, I'll just write down the mechanism also for you. It is a classic E2 mechanism as they call it. I have Br, I have CH3, HH, HH, and let's take it like this. See, we have OET minus. It attacks a beta hydrogen. That means it donates a lone pair. This hydrogen leaves its electron, comes here, and it pushes out the halogen like this. Oh my God. This is the way? Yes. So this is beta hydrogen, this is the leaving group, and this is alpha carbon. Alpha carbon, alpha hydrogens, and this is beta hydrogen. What do you get? You get an elimination product like this. Okay. Where did the hydrogens disappear? They are very much there. They have not disappeared anywhere. Just that. Explicit hydrogens don't have to be written in bond line notation. You may write it, you may skip them. This is what we get. Okay. And what happens to this? You get ET, OH, fine. and Br minus, of course. Done? Done. Sorry. Is there a minor product also? Yes. And what is that? I'll show you that also. You have Br, yes, and you have CH2H. Okay. So I use EtO minus. Donate, jump, push out. You will get this is also a reaction possible in case you have something which we were calling beta 3. 1, 2, 3 is arbitrary name given by me. There is no standard nomenclature there. Just to indicate that there are different betas. Now, I have this and I have this. Which one is going to be the product? Which is the correct answer? Honestly, each of these is possible. But then in organic chemistry, there is a concept of major and minor. Always you get something which is more favored and something which is less favored. This is major product and this is minor. In this case, major and minor was dependent on beta hydrogens. If you have 3 different types of beta hydrogens, you get 3 different types of products. So it's as simple as that. In our case, we had beta 1 was same as beta 2, beta 3 was different. So I have 2 types of products. Okay, that's fine. Anything else? Well, I guess that's it. Major and minor. Why is it major? Why is it minor? There is a rule, as I said, called Zaitsev's rule. Yeah, more honestly, Zaitsev's rule. Both are same. Even the person is same. Now, what is the rule? It says that the more branched alkene is the more favored alkene. If you are getting 2 different alkenes, then the alkene with more branches is the major product. How do I decide the number of branches? That's not very difficult. Just look at this. This is the alkene. Yes. What about branches? See, these are vinylic carbons. Now, 1 carbon, 2 carbon, and 3 carbon. This vinylic carbon is linked to 1 and 1, 2 carbons, and this is linked to 1 carbon. The 3 carbons. These carbons I'm talking about. So we say it is branched in such a way that it has 3 neighboring carbons. What about this? This alkene is branched in such a way that it has 2 neighboring carbons. It has 1 and 1, 2 branches. This has 1, 2 and 3 branches. More branched alkene is more stable. That is Zaitsev's rule, and more branched alkene is more favored product. So this is why this is the major product and this is the minor product. Second question mentions, now you have to solve this. You have 2-chloro-2-methyl butane. Now I have butane, I have methyl and I have chloro. Fine. Like this. Can I mark alpha and beta carbons? Yes, I can. Cl is here, so this is alpha carbon. The carbon attached to halogen is alpha carbon. The neighbors are beta carbons. And I have not 1, not 2, I have 3 beta carbons. What should I do? As elimination happens, I'll start getting different alkenes. With beta 1, if I remove hydrogen, I get a pi bond here. This. With beta 2, I get a pi bond down there. Actually, if you see, these are same. These are identical, there is no difference. So beta 1 is same as beta 2. What about beta 3? Let's try that. If beta 3 is eliminated, well, what you get is this. Oh my God. Now, just look at the level of branching. In this case, you have 1 and 1, 2 branches. There is no branching here. In this case, you have 1, 2 and 3 branches. This is good. This is great. Yes. So this naturally becomes the major product, and this is the answer. What are these? These are minor products. Fine. They're not even asked, but I've just mentioned them for your information. Now the third part. It says, well, we have pentane, 3-bromo, 2,2,3, trimethyl. Okay. This is the structure. Very interesting. Now, let's identify alpha and beta. This is alpha carbon, right? So this is beta 1, this is beta 2, and this is actually, you could say beta 3, but there is a problem. Carbon, 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 carbon. There is no beta hydrogen here. And if there is no beta hydrogen, obviously you can't eliminate from here. There has to be at least a hydrogen, right? So this is a quaternary carbon with no hydrogen. Already carbon has formed 1, 2, 3, 4 bonds with 4 different carbon atoms. There is no hydrogen atom here, so you cannot form a pi bond on this side. You can't make a 5th bond here. So only beta 1 and beta 2, I get 2 products. With beta 1, I can just write down elimination. How would that look like? First, let me write down the molecule. Well, this is pentane. With beta 1 elimination, I get this. With beta 2, I get this. And now the question is, which is more branched, which is more stable? This alkene has 1, 2 and 3 branches. This alkene has only 1 and 2 branches. There is no branch here. So this becomes the major product. And this is the answer. Yes, this is the answer.